And so I thought I would start actually with some motivation, and then I'm going to turn to the board and do some calculations of some prototypical problems. And I was very fortunate that we just had the lecture that we did, because I'm going to be talking about inextensible rods with bending rigidity. So it kind of set that up perfectly as one of the examples of kind of the way in which we construct models and use them. Okay. So, but I thought I'd give, as I said, some motivation as to why we look at these things. And so here's one. This is one of my current favorites. So what you're seeing here is time snapshots. I think this is over about the course of half an hour, something like that. So call those 5-minute intervals because there's 6 pictures. So what you're seeing here is a single cell embryo, and it's of an organism called C. elegans. It's a model organism. It's a little nematode. In its entirety, it's about 1,000 cells. It's about 1 millimeter long. And biologists, laboratories all over the world study this little guy. And what you're seeing here is what happens when its embryo gets fertilized. And so actually this is rather late stage stuff, but so right here you'll see my point here in just a second. What I really want you to focus on are these little star-like areas here where you see this very bright spot and then these radial lines that are going out. What those are very small biopolymers called tubulin. Here's tubulin down here in some sort of schematic form. And it's made out of dimers, tubulin dimers. And when it polymerizes and forms a polymer, we call that a microtubule. And the cell here is filled with microtubules that are polymerizing from these bright spots in that picture. And so inside of this cell is this very thick, soupy, it's called a cytoplasm. And so what has to happen, the prime function of what's going on of all this machinery that's inside the cell, is it wants to get the male and female pronuclei, which are the left is the female, the right is the male. It wants to move that material into the center of the cell. There it's gotten into the center. It wants to rotate it so that those bright spots are lined up with the long axis, kind of like they are here and here and here and here. And then something else is going to form, also made out of microtubules, called the mitotic spindle. And that's this kind of area in between here. And the mitotic spindle is the physical structure that forms inside of these cells so that the chromosomes, the duplicated chromosomes, can be segregated, moved to opposite side of the cells, and then you can divide that cell and have 2 copies. And then you keep repeating this process slightly differently. Time and time again. But the main point here is that there are a lot of what's going on. Maybe I'll talk about this in my last lecture, mathematical models for how this actually happens. The first part, how things get moved into the center of the cell. A lot of this happens because you have these long, skinny objects that are immersed into a fluid upon which motor proteins can attach themselves and move along it. And that's a way of doing force transduction, it turns out. And so there's an example. It's a very complicated, what you would call fluid structure interaction problem. It involves long, skinny objects that are essentially inextensible elasticae, Kirchhoff rods, if you want. So another example, biofilms. This is something that Howard's group has worked on a lot. I call it the ubiquitous biofilm because if you start to read about them, you will find, much to your alarm, that they're everywhere. They're all over your body. They're all over everything that you might touch. Everything is coated oftentimes with a film of bacteria that are amalgamated together in certain ways. And when they're in flows, they can form long elastic streamers, actually, of biological material that get drawn out in the flow. And this is an experiment, I guess, of growing a biofilm streamer coming from Howard's lab. So this is another example, and these are also essentially kind of elastica. Again, immersed in a fluid, which, because it's very small scale, you don't have to pay attention to inertia, and you're just talking about the Stokes equations. Oh yeah, so This is actually a cheat. I just wanted a good picture of a biofilm in nature. So this is actually in a shallow stream that's in the bottom of a copper mine in California. And you get these biofilms that have formed streamers. It's a really beautiful picture. Whether it's small Reynolds number, maybe not, because this is about a meter. So, but I thought it was a great picture. Could have almost as well come from a microscope. Another place where you find long, skinny things doing interesting things, though maybe less long and less skinny than the two previous examples, has to do with microorganismal locomotion. And here's a few examples. Let's start down here. This is actually the mature C. elegans that we were looking at the single cell embryo before. And this little worm just propagates bending waves through its body from the head to the tail, and in that way propels itself forward. And someone asks, when can you start using the low Reynolds number flow approximation, namely dropping inertia? This is about an order 1 Reynolds number, and it's pretty well described by the Stokes equations, actually. So order 1, 0.1, something like that, it's good. This is another example. So these are circulating vortices that are actually made up of a lot of individual long, skinny objects that are swimming around. In this case, it's bull sperm, spermatozoa. And when they get at high concentrations, it turns out that there is some synchronization that takes place. Again, this swimmer is moving bending waves. Essentially, it's an actuated elasticae. You might think of it that way. It has a certain intrinsic elastic behavior, but it's also actuated. And so you can have these bending waves get synchronized with each other, apparently, and when that happens, you can get circles of them going around, and you pack them in tightly enough, and these circles start to abut upon each other, and they start to order into some sort of kind of loose hexagonal ordering. There's some very beautiful work, actually, that came out of Ray Goldstein's lab last year or the year before. This is actually a little dish that's full of swimming bacteria, Bacteria subtilis. And so Bacteria subtilis is essentially, it's a rod-like bacteria. There's one up there, which is looking rather long and rod-like, especially so because it's about to divide, so it's a bit longer maybe than it usually is. But it has a long, when it's swimming, it has a long tail of flagella that increases its effective length, so you can think of it as a long thing where part of the long thing is actuation for propulsion and the other part is the payload that's being pushed forward. And when you put them at high concentration in a dish, you find you can form these kind of swirling vortical patterns. And you have very interesting kind of differential rotation rates as you look at what goes on inside. Okay, so those three are all from biology, but it turns out that there's lots of interesting things to do with long, skinny objects. They arise in industrial processes. A very classical example are wood pulp suspensions. So you have these kind of slurries where you have these small wood fibers immersed in the slurry, and they have very interesting kind of mechanical responses. Perhaps it's something that Anke will talk about in a few days. And so it's become kind of a big activity to try to create kind of controlled suspensions of long elastic particles. And so this is from ESPCI, from Anke and Olivia, various ways in which one can fabricate different kinds of elastic particles to start to play games with them in other kinds of experiments. So this is a little rod that's been created through photolithography. This is it's magnetic chaining, I think, right? So an irreversible way of chaining together beads together in a little microfluidic cell. And this is a actin polymer that's being formed through polymerization from actin molecules kind of sticking themselves together into a long chain. Then when you have these, you can start playing various games. And so this is the dynamics of an elastic rod, an experiment from Anke's group. This is showing the dynamics of, and this is buckling right here. This might be the first instance we've kind of talked about buckling a little bit in the last talk, but this is a real case where you have a rod that's moving around inside of a cellular flow. You can see the streamlines of the flow. This is from an experiment that's being driven by magnetic rollers. And so you have a little layer of fluid, and this rod is floating around on the surface. That fluid is driven into rotation in kind of sets of counter-rotating cells. And so here it's kind of moving along. It hits a stagnation point, and I'll talk about this problem later. It hits a stagnation point, and you have to ask, where do the stresses come from that cause something interesting to happen? In these types of systems, when you think about having elastica, the classical problem is that you imagine that the elastica is end-loaded, right? And so you have an elastica, and you have forces on the end, and you're pushing it, and then you're looking for a bifurcation to a buckled state. These cases are the same but different, because here what happens is when I have a free particle, a free fiber that's floating around, moving around in a fluid, it experiences viscous stresses, right? So I have the fluid is perhaps shearing across it, or some sort of straining along the fiber, and so you have surface loading where the viscous stresses are maybe compressing or extending it because this guy is in some sort of background flow shear. And so these are all kind of surface loaded types of buckling events. And so what happens here is this fiber approaches a stagnation point of the flow along the stable streamline into the stagnation point. You get you get a viscous loading on the surface, it buckles, and then it goes off somewhere else, buckles again, straightens out, and so on. And so this is actually a very beautiful kind of nonlinear dynamics experiment where you can take elastic fibers, you can immerse them into essentially a viscous flow. They have internal degrees of freedom because they're elastica, and these internal degrees of freedom let them interact with the flow in very complicated ways. This is another example. This is the Canceller experiment, I believe. These are actually actin filaments that are being held in a microfluidic device at a stagnation point. So there's a kind of a cross-shaped little device where you're flowing in fluid in one direction, you're pulling it out in the other, so you have a stagnation point sitting there right at the cross, and there's a little tiny actin polymer that's being held at that stagnation point and looking at various buckling modes as you change the strength of the flow, as you're changing the amount of viscous loading. Again, this is from Anke and Olivia. This is a elastic fiber moving into a constriction, showing how it can get caught and then go into I wouldn't call this buckling, I would call this bending. So it's moving into some sort of bent state. And then one last example is, this is one of my favorites, really. This is quite aged on kind of the scale of this field. But this is from Peter Palfy-Mahore at the Liquid Crystal Institute back in the States. And this is a picture through a microscope of a pattern that forms because I have a liquid crystalline fluid, which is, say, if it's warm, okay, it's in an isotropic state, it behaves like a regular Newtonian fluid. But if I start to cool it, it goes through a phase transition. And how many people in here know what a smectic phase is for a liquid crystalline material? Okay, a lot of you do. So those who don't, then you can ask the person next to you and they'll tell you what it is. So what's going on here is that this has been undercooled. And so it's below this phase transition temperature, and it wants to move from being isotropic to smectic. So in a smectic phase, you have a bunch of rod-like molecules. They want to line themselves up into layers, so-called molecular layers. If I have a bunch of layers with all the rods sticking like this, kind of stacked up, and I bend that layer, I get a bending response. It's like an elastic sheet. I'm causing these molecules to splay out like that, and they want to come back. So it turns out that these line up into molecular layers that are actually lined up as kind of tubes around a center line. So you just have a long tube that has molecular layers that are arranged like an onion skin, like an elongated onion skin around the center line. So it's like an elastica, which is formed from this very soft material that comes from an isotropic phase transition. And so what happens is that, I'll come back, these are all words, and I'm literally waving my hands around trying to describe this to you, but I'll describe it to you again later perhaps. But what happens is I have an elastica, and now just think of it as an elastica, and this elastica is growing because in the phase transition problem, there's material permeating into it and moving into this smectic phase. And so it's growing like this, and it grows despite the fluid drag that has to be overcome to extend its length. That creates, again, a viscous loading on the surface, which creates a negative tension inside, and that makes it buckled. And so what happens is that this is the buckled pattern that you form, is kind of a space filling pattern of this kind of buckled structure as this kind of boom, 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 as it's undergoing this phase transition. This is actually the problem that got me into thinking about long, skinny elastic objects and flows, was exactly this problem. Okay, so what I'm going to do is I'm going to jump forward very far, and then I'm going to jump back. And so I think, are you going to talk about boundary integral formulations? Okay,
yes,
good. Good.
Yeah,
excellent.
But it might not be till the 37th.
It's okay. You know there have been educational studies that show that if you don't always follow a nice linear path, then that can actually be good for education. Yeah. So that's what we're doing. And so what I'm going to do is not even outline, but just kind of tell you what the elements are by which you would go from something that's called the boundary integral formulation for solutions to the Stokes equations in the barest of schematic forms, go directly to the asymptotic result that says, how do I describe a long, skinny object moving in a Stokesian fluid, Newtonian fluid? And then I'm going to take that and I'm going to simplify it to its barest form, which is basically just a linear PDE for moving the center line of this object, whatever that is, and then just go from there. And then we'll come back to the more complicated things in later lectures in the school. Okay. So let me set up some preamble. So these, every one of these is, a long, skinny object moving around in a Newtonian fluid, except for one picture, which I'll bet nobody knows where the fluid's actually not Newtonian. Okay. Yeah, that little guy up there, I stole that from some other paper that actually is a viscoelastic fluid, but I didn't think anybody would catch me.
It's tough with a snapshot.
Yeah, that's right. So here's what we're talking about. So we're talking about bodies, and here I've done the spherical cow as usual. But here we're talking about bodies that are immersed inside. So just consider this some sort of solid body, and it's moving with some velocity. So its surface has some velocity. I'll call U body, and it's also exerting some sort of stress on the fluid. So I'll call that G. And what I want to know is those two items are not independent of each other. They're actually related through the Stokes equations. But let's say I was given one. Let's say I was given the velocity of the body. I would want to know what's the Stokesian fluid motion outside of that body. And for example, what is the surface stress that's a consequence of that particular body motion? So what we're doing is we're solving. There's the Newtonian Stokes equations right there, written in a. I think Howard wrote this down exactly this before, though I hope our notations are the same. I have a divergence of a stress tensor is 0. That means I'm ignoring inertial forces in the material. I'm going to assume that I have a divergence-free velocity field, and my stress tensor is just an isotropic pressure stress plus 2 mu times E, which is the symmetrized rate of strain tensor. So 1/2 grad U plus grad U transpose. And then I have the conditions the no-slip condition, so to speak, the velocity of the fluid is stuck to the body, so it moves at the same velocity, and that the fluid stress on the surface is matched by the stress being exerted by the body. I might need a minus sign in there, but okay. Okay, now, so this is a boundary value problem. Why is it a boundary value problem? That's because Howard went over this. It's essentially a biharmonic problem, okay? But this is a constant coefficient, constant coefficient set of biharmonic equations, essentially. And so if you were dealing with just solving Laplace's equation, and they're homogeneous. I forgot to say homogeneous. We like homogeneity. There's a 0 on the right-hand side. Then if I was solving Laplace's equation with some boundary data, say a Dirichlet problem or a Neumann boundary condition problem, I would want to use maybe some distribution of sources and dipoles to describe that field on the surface. And so you do the same thing in the Stokes equations, and it's a little bit more complicated, but the first thing you need to do is you need to construct some free space Green's functions. So you throw a delta function of force onto the right-hand side of that. You solve the Stokes equations in the presence of a delta function of force, and that generates some free space Green's functions. And here's one of them, the so-called Stokelet, written down now in indicial form, which just says this is a solution to the Stokes equations. That's the flow that's generated by a vector that is, say, pointing in some direction ek, so you'd contract this against the kth component of the direction your delta function was pointing. And this is the flow that gets generated at decays like 1 over r as you move away from the point source. There's an associated delta function for the stress tensor. That's what that guy looks like. Okay, you'll see all this later, so-called stresslet and Stokelet. There's rotlets, there's all sorts of things. So what you do is you use an identity called the Lorentz identity. And again, I think you'll see this in great, I hope, great detail in Howard's stuff, because this is very important stuff for working with the Stokes equations. And this is going to show you why right here. You can use the Lorentz identity to find a linear but non-local relation between the velocity and the bulk at some point y. So here I am, it's off the body at some point y. And versus the surface stress integrated, convolved on the surface against the Stokelet kernel. Okay, so that's a convolution, a surface convolution, plus the surface velocity convolved against something involving this stresslet Green's function itself contracted against the normal to the surface. Okay, so I have this relation then that says if I know my surface velocity and I know my surface stress, I can tell you what the fluid velocity is for the solution to the Stokes equations at any point outside in the fluid. Is that nice? Of course, it's beautiful. Now, why is it beautiful? here's the kicker. I can take this point y, and I can move it to the surface. Okay, so I derived this equation from the Lorentz identity under the assumption that the point y was away from the surface somewhere in the fluid volume. So I move to the surface. I take the limit x goes to the surface on the body. I have the no-slip condition that says that the velocity of the fluid has to match the velocity of the body, right? So this guy over here has to go to the surface velocity. This guy is what you would call a double layer integral. So this is in the parlance of integral equation methods. This is called this first guy is a single layer, and that's a double layer. The double layer in that limit pops out another contribution of the surface velocity plus a principal value integral. And what I get in the end is on the surface, I have a relation that relates the surface velocity, these guys, ui and uj, to the surface stress. So for example, if I know, this isn't the best way to do this particular problem, but if I knew what the surface velocity was, then I could use this as a first kind integral equation to determine what the surface stress was, right? So then I would have solved exactly the relation between the surface velocity and the surface stress. I stick it back up into here, and I've solved my problem. I know my fluid velocity everywhere. I've determined what the relation was between these two quantities, surface velocity and surface stress. If I know what my surface stress is, this becomes a second kind Fredholm integral equation for the surface velocity. So in the other parlance, this is the identity plus a compact operator. How many people have heard that phrase before? Identity plus compact operator. Okay, so, so 20 of you can ask these two what that means. And basically means that's a really nice equation to invert. It essentially looks like a finite dimensional problem.
But you're thinking about a rigid body, U is a constant in that case? Or
No, not necessarily. G.
So U could be a distribution.
Yeah. So it might be deforming, and there. Yeah. Okay. So so my point is though that what this does is it reduces solving the Stokes equations from something where you have to. So if you're, how many people here have taken a CFD class, computational fluid dynamics? A smattering of you. Well, usually with the Navier-Stokes equations, you have to resolve the whole volume, right? And you have to evolve things in the volume. You have your inertial term, and you determine the pressure, all this stuff in the volume. When you have these types of problems, which are boundary value problems, you don't need to solve in the volume. You just solve integral equations on surfaces. And then you construct the volume. So the point is that this reduces the dimensionality of the work you need to do by 1 dimension. Okay, so that's a huge relief in terms of how much work you have to do computationally. So this is why they're so, for other reasons, they're very important. But the main point is it shows you that you can reduce the computational effort from a 3-dimensional problem to a 2-dimensional problem on surfaces. Okay. Now, you'll hear about how all this is done, and more, I think. But what you can do is that when you have a long, skinny object, you can simplify this thing enormously. Okay? And this is work, this is a very classical area in the Stokes equations. And Lighthill's worked on this problem. Many people have worked on this problem. I think the cleanest formulation of, now, so this is called slender-body theory. So now I imagine that my body is not this kind of compact thing, but it's a long, skinny thing, which looks essentially like a center line plus some outer wrapping, which is in cross-section just circular, though you can generalize that as well. And so then it turns out that in the formulation of assuming that I have a long, slender object, so here, there it is, I have a center line. Bazille drew a center line in the last talk. Here's another center line contribution. And I have a center line, and the body surface is some sort of just circular shell around it, following the center line. And that stress gets communicated to the fluid in this asymptotic reduction of being a long, slender object in terms of a force per unit length. You get, in the asymptotics, you get to integrate that stress around the body. You integrate it azimuthally. So here you're talking about a surface essentially exerting a force per unit length on the fluid. And I'm going to describe the center line by its arc length. Okay? So there it is, x of s and t. It turns out that what happens is that asymptotically, this piece right here, this so-called double layer term, is asymptotically small relative to this term. Okay, so this one goes away. The first 2 leading orders of the asymptotics. In small epsilon, what's epsilon? I'll say that again in just a second. I should have said it already here before. Epsilon here is the radius of this object divided by its length. Okay, so I'm assuming I have something which is much longer than it is thick. And I use that as an asymptotic parameter. And so what it tells me is if this object is moving around in some background flow u, so here now it's motion against a background flow, maybe it's being generated by other objects like it, or maybe I'm shearing a cell or something, but there's some background flow. And then it says that the motion of the center line, the velocity of the center line, and here I'm already assuming, which I will assume henceforth, that the arc length of the center line is going to be a material description, okay, of the center line. Let me back up a little bit. What does that mean? Well, I didn't have to assume that, but let's say I do right now. What does that mean mechanically? If I have a curve, so I put some sort of string into a fluid, and I mark little ticks along it, evenly spaced in the arc length, and I say that those are material points. What's that? It's inextensible, right? So that's saying that the arc length is a material description of the curve, which means, since it's arc length, the distances between material points can't change differentially. So that means it's an inextensible object. Okay, so we're going to be dealing with inextensible objects. I didn't need to at this point, but let's just say we are. That's why I have this ddt here, because here I'm holding s fixed, and I'm saying that's a velocity, right? Okay, so then the velocity of the curve relative to the background is some integral operator acting on that force per unit length, which is this azimuthally integrated surface stress. And that piece comes in 2 parts. You can separate them out. One is a term which is purely local. What's s hat? S hat is just the tangent to the center line, so it's dx ds, right? It's the position with derivative of position with respect to arc length, hence it's a unit vector. I call that s hat. I will never call it s hat after this, I'm sorry. But it's some constant c times a little identity plus a rank 1 tensor. That should be ss transpose, okay? Acting on f, so this is purely local, plus an integral operator. And this integral operator is this kind of horrible looking thing, which comes from the matched asymptotics that Joe Keller and Johnson, Gutz, many people have worked on deriving this formula in different ways. Some from matched asymptotics, some by using an ansatz of a singularity distribution along a center line, some by starting from that Lorentz identity generated integral equation and doing asymptotics on it. But here's what it looks like. And then we're going to forget about this for a while. I have 2 points on the surface. They communicate to each other through incompressibility and the Stokes equations, right? And so this is the way they communicate to each other. There's this, it's essentially a Stokeslet kernel right here, which has been regularized. You don't really need it. I don't want to spend too much time on this because this is a very technical slide from a technical talk, and we're going to drop it all here in a second. And this is some other term that makes this, if I just had this object, if I set this delta to 0, right, then it turns out that this guy, that's a divergent integral, okay? And so this makes it a finite part integral. It's actually something that you had to add and subtract in order to generate this leading order term in the asymptotics. So let's not worry about what that is, except to say this is an order 1 operator in terms of epsilon. That's the only thing I want to say about it. It's an integral operator and it's order 1. This local term has this constant c in front of it. That's also an asymptotic parameter. And there's what c is. C is minus the log of epsilon squared, that's my small parameter, times e. The constant e, 2.71, whatever.
And
okay.
ln means natural log or log?
That's natural log. Natural log. So, -1, expand it out if you want. Okay, but my main point is that in this expression here, this term is logarithmically large. That's the asymptotic ordering. This term is logarithmically large, and this term is order 1. And the next term is order epsilon squared log epsilon, it turns out. Okay? Which I've dropped that. So what I'm going to do is just take we're just going to play because it's it's a very, very useful model, and it's asymptotically consistent. What we're going to do is just play with this so-called local drag model. We're going to drop this order 1 term and just keep this logarithmically large term here. Okay? And so this is the one that says, oh, I have a fiber or a curve that's immersed in an incompressible fluid, so if I move something here, it gets communicated here. This is the term that tells you how to do that in the context of the Stokes equations. Okay? And this is a term that says at leading order, logarithmic leading order, this is what governs the dynamics, and that's the local drag model. It's extremely popular, so Howard alluded to it in terms of the drag on bodies that are falling in the direction of they always fall in the direction of gravity, but whether they're lined up with gravity or transverse to gravity, they have different speeds. So we'll talk about that. That's built into this.
And the spherical limit will be
the what?
The spherical limit.
Oh, well, yeah, there is no spherical limit here. This is all long wave asymptotics. Okay. So now I'm going to move to the board.
I guess you might do.
Yeah.
If you played with your I plus SS and somehow made it. So if you just took that away, I guess you have a spherical limit. It would be all inconsistent.
The problem would be this term.
Oh, I wasn't thinking about that. I was
Yeah.
thinking about your local drag model.
Oh, no, that's true. Yeah, that's right. Then you just make sure your C is the right thing according to Stokes's equation. Yeah, that's right. But the rest of this screws that up. The integral part screws that up. It's all one-dimensional integrals. That's right. So this is one of the absolute standard models of low Reynolds number hydrodynamics, local slender-body theory. And that's because people wanted to understand things like microorganismal locomotion, where you move into the limit where you think of microorganisms as being long, skinny things, okay, for example. Okay, so here's what that leading order bit looks like. Let me draw the picture here. So I imagine I have a body that I'm going to describe by its center line. There's some technical aspects that have to do with what you do at the ends, but we will ignore that. The kind of operative papers, let me just say, are Keller and Rubinow. And that's JFM in 76. And then Johnson. And that's JFM 1980. Okay? Let me just say that I made this whole comment about what goes on at the ends. That's often where asymptotics breaks down. And what Johnson did was corrected something Keller and Siegel had done to make sure that the ends were treated correctly in the asymptotics. Okay, but I have a body, and I'll assume it's circular in cross-section. And so this point right here is x of st. Here we'll call this s equals 0, s equals L. So I'll have some length, L. And I have a center line, and I have a radius, R of s. Okay? And so the asymptotics is built on taking the small parameter epsilon, which is equal to R of L upon 2, so the radius at the center over L, and assuming that that's much less than 1. Okay, so there's your well-defined small parameter. Okay, so local slender-body theory is the following equation. I heard a question.
This is a stupid question. So this
It's okay.
radius is not constant all over.
Not necessarily, but I'm going to assume essentially it's a
Say
constant.
that in your case it will.
Just call it R. Just think of it as being constant. Yeah. There's lots of details, or people have worked out lots of details, but they're kind of unimportant to this.
Right here, you will impose the central radius much less than 1.
Right. So there's other kinds of assumptions that you're making, which you can think about what they must be as we go along. Okay. So here's the equation. Eta, I'll say what eta is here in a second. So here mu is the fluid viscosity. So eta del x del t of s and t minus, oh yeah, so this guy is sitting here in some background flow. U of x and t. It doesn't have to be a shear flow. It could be something more complicated. Now, this is where you should start thinking immediately. What else am I assuming? I'm assuming that the length scales of that background flow are large relative to the radius of this object. That's an assumption that's being made. So that's the left-hand side. So this is, if you like, this is the drag this is the drag force that's induced by motion relative to the background flow. And here's that I plus s hat, and I'll drop that s because it's inconvenient. And I'll write this as I plus xs transpose, acting on that force per unit length, F. Okay? So that's local slender-body theory. What's eta? Eta is 8 pi mu over minus c, where c was that logarithmically large term. So it's minus, no, okay, I already, too many minus signs. It's log of e epsilon squared. So minus c is positive. Okay? So this is proportional, though, to the viscosity of the fluid.
Excuse me, how does this C come from?
That comes from the asymptotics that takes you from that surface integral expression into one which is just along the center line. I'll refer you to these papers if you want to see where it comes from. Howard, where was that button?
Underneath, on the right. Behind you, turn around. There, the white, the plastic interior. There, this box. This box.
Oh, this.
That's that first one.
Okay, thanks. Sorry to sorry to get you out of your seat. Yeah. Yeah, that's right. That's a wave. There's a convective instability. If we wait here, this thing will have moved a centimeter by tomorrow. Oh, I meant to number some things. So just the various parts. I already told you what that eta was. So let's call this term here 1. Let's call this tensor 3. I've already said a lot of this. And I'll call that equation 1. Can I get this to go up more? No, that's it. The shadow is a little unfortunate. And so 1, this is not quite accurate, but it's accurate enough. Okay? So 1 is the drag force for motion relative to the background flow U. Two, this is the force per length exerted by, now I'm going to call it the fiber. That's suggestive, of course, of elasticity. I don't mean it to be necessarily, but I'll just call it fiber. The force exerted by the fiber upon the fluid. In 3, this states drag is anisotropic. Now, that's why I said this first part was a little incorrect. I should have this guy over on the other side and then call it the drag force and then say the drag force is anisotropic. But anyway, this is just the way it's usually written, so I'll leave it like that. Drag is anisotropic. Okay? So let's just think about that for just a second. So here, in this expression, I have two directions, right? I have the direction given by the tangent vector, and I have the direction of the force. And those two directions can either be lined up with each other or not. Typically, they're not, generically, but let's take the two extremes, where F is in the direction of the tangent vector, okay, versus F being orthogonal to the tangent vector. So let's say that F, just to be specific, looks like, you know, the gravitational vector. I should put something in there to give it the right scaling, but I'll just put an alpha there. That'll do it. So I have a gravity pulling things down, okay? And let's say that my fiber is not density matched, so it gets pulled down by gravity. You need to be a little more careful because it's density differences and not bare masses that matter. But my alpha takes care of all that. And so then the point is that if xs, yeah, so this guy I'm taking to be a unit vector, so I might as well just call it y. There we are. F points in the y direction. Okay, let's make it easy. So let's say xs is in the y direction, right? So then here, that means that xs dot f is equal to alpha. So what I end up getting here is that, and let's set u to 0. then what I end up getting here is that del x del t is 2 alpha y hat. Okay? On the other hand, I could have taken f, say, be equal to f x hat, orthogonal to the direction in which, oh no, I'm sorry, let me do it the other way. We leave that, and instead we'll say that's case 1. Case 2, we'll say xs is x hat. So now the fiber is laying sideways relative to the applied force. Okay? Then x hat is orthogonal to xs, so that guy's gone. And in that second case, I just get del x del t is alpha y hat. So that's that factor of 2 that Howard was talking about, that you see exactly a factor of 2 in this asymptotic limit of an asymptotically slender rod. Okay? So what that means is that forces that are directed along the rod axis get twice the velocity, so to speak, as ones that are orthogonal. Okay? That's drag anisotropy. Drag anisotropy is right at the center of why many microorganisms can actually move. Even though if I have a free particle that's density matched in a fluid, it can exert no force or torque because I'm in this inertialess limit. It's drag anisotropy that lets that happen, lets things move despite exerting no force or torque by their motions. Okay. And I already said what eta was. Okay. Now, it's kind of a sick sound. This is a tired blackboard. It spent years in service. Hundreds of people have sat in front of it, and it's getting a little tired. Year after year, dragging itself up and down. Okay, I erased my prime equation. There it is. Okay. So, what kind of forces might F reflect? Okay? And so this is now a modeling choice. Let's say that, so here's 2 basic flavors. One that reflects internal mechanics of elasticity, and another, say, that reflects the internal mechanics of constraint. Okay? So for example, let's say I assume, and this is actually a good problem to work on in your off hours, just to think about this problem. Assume the fiber is rigid and straight. So rigidity means I can write down an ansatz, a simplified ansatz for how the center line must look. So then I can say, oh, I can always write then the center line in the following form. I can write it as the center of mass position. So it's a vector indeed. Thanks. Is the center of mass position plus the arc length times an orientation vector. And here, yeah, so there it is. I'm going to change the definition of S so that it's assigned arc length. So S equals 0 locates the center of mass. Okay? So here then, there's XC, And then that direction is this unit vector E hat. And so mod E hat is 1. So then, let's say I'm in a background flow. And then this is going to be a problem I want people to work out, actually. Okay? So let's say I'm in a background flow. So I put this ansatz into my equation 1. Notice I've already built inextensibility into the formulation, into the ansatz of the center line. Right? So I separated S and T in this way. And so then I have eta xc dot plus S E hat dot minus U of xc plus S E hat T is, now here I should also say, xs, of course, is just E hat. Right? That's just my tangent vector. And then this is equal to I plus E hat transpose times F. Okay? Oh, you know, at Courant we have, yeah, I'm going to try not to join Howard in complaining too much about the board, but no, not at all. So, but I'm going to keep trying to lift the board because we have the same kind of setup, but they're on these pulleys, these counterweighted pulleys. You just pull them up, pull them down. So I'm going to keep trying to get them to move. Now, I just want to make a comment before I keep going. And it's the following. In the absence of a body force, say gravity, or in the absence of any density difference between the fluid and the body, so that's what we call density matched. Now there's a conclusion, obviously, to this sentence. What's the conclusion? The body cannot what? Cannot move. It's going to move. I have a velocity field in here. It's going to make it move. But well, no. Let's say I have a rod that's in a shear flow. It's going to rotate. But because, let's say that rod is density matched, so it's not going to sink or anything like that. What that means is that it can't exert any net force or torque on the fluid. Okay? Why is that? It turns out that it's exactly the same argument as the low Reynolds number argument that tells you can throw away the inertial term in the Navier-Stokes equations. It's the same argument. And that's because what gives you a force on the body involves the stress tensor. And when you do the non-dimensionalization that gives you the Navier-Stokes equations, you introduce a Reynolds number into that stress tensor, which is the total force that the body is exerting, related to the total force the body is exerting on the fluid. So you end up getting a Reynolds number floating over to the left-hand side of the acceleration of the body. So you take the low Reynolds number limit, and it turns out you're left with saying that the total force of the fluid upon the body, or vice versa, the body upon the fluid has to be 0. Okay, so then blah, 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 in the absence of any density difference between body and fluid, the total force or torque upon the fluid in this inertialess limit must be 0. That's an exercise. Okay? See if you can show that. What that means here, yeah, I heard a question.
Well, you're setting your, are you saying you're setting your F to be 0?
No, I'm setting the integral of F to be 0 because that's the total force. So in this case, what that means is the total force that the body is exerting upon the fluid. In this case, in this slender body case, is the integral with respect to arc length of F of S and T. Okay? And this has to be 0. That's a constraint. That's one constraint. Second constraint is that the torque integral minus L over 2 to L over 2, x minus xc cross F, that has to be 0. I try to be religious about making sure things are vectors. Okay? So here's the exercise. So exercise 1, show that, just take a rigid body. I don't really care. Make it easy. And show that this follows from the same type of scaling analysis that leads to the Stokes equations from the Navier-Stokes equations. The second, there's a whole point to all of this. You're probably thinking, what the hell is he talking about up here? The second is I've set up a problem, it turns out, where the force is going to be determined, whatever that F is, that force is going to be determined by 3 things. Here's 2 of them, plus the constraint that X has to have that form. That's the constraint. I am constrained to have this geometric form. Now the question is, what is F? I've given you all the information to calculate it, and then also calculate what xc dot is and e hat dot. Okay? The point is that this guy is geometrically constrained, and under the constraints of 0 force and 0 torque, you can determine what the motion of the center of mass is and the rotation rate. Okay? The internal mechanics are mechanics of constraint. You see what I'm saying? There's no bending, anything like that. I'm saying I remain straight. So, determine F, xc dot, and e hat dot. Okay, it's just some algebra. If you end up with an expression that does not involve integrals, you've made a mistake. Okay.
And the 3 equations, just so I understand, somehow I feel like I should present. The equations you have to work with are 3. You have the one on the right, lower right.
Wait.
You have your xc dot equation on the upper board.
Sorry, yeah, right here. Yes, thank you, Howard.
You
have this,
and then you have your 2.
and then I have my force and torque constraint. Okay? It turns out that this guy generates a set of ordinary differential equations that are really fun to play with numerically. Okay? Do you think, Anke? No, she doesn't. Yeah, okay, I thought it was fun. Okay, so that's one. These are, if you like, these are forces of constraint. Force is a constraint force.
Can I ask, does the equation for xc separate from the ones for e hat, or are they all coupled?
It does, actually. Or, I'm sorry. Now I have to remember. No, it doesn't completely decouple. Or rather, I should say you can write down xc dot and e hat dot, but they depend on xc and e on the right-hand side. But yeah, you can separate them and find them.
So they are separate.
They are separate. Yeah, I misspoke. It's the xc and the e hat that mix on the right-hand
And
side.
the e hat is the Jeffrey problem?
Yes, if that were a linear shear, it would be the Jeffrey problem. This is more complicated. This is just say, given any old background flow. Yeah. Okay. So there's lots of cases. There's lots of cases where this is an interesting problem to solve. Why might it be interesting? Let's say that I have a wood pulp suspension where the fibers are really rigid, so I can treat them as straight, right? I just ignore the bending rigidity. I just say they're straight and inextensible. Then this is the formulation you would have, where this U would be the flow that might be generated by the other fibers moving around, right? And so this is kind of the basic piece you have to get. You have a fluid mechanics problem where all the forces you're determining, because your particles are rigid of this sort, they're all constraint forces. Of course, you might say, oh, big deal, many solid particle suspension dynamics problems look like that. Well, yes, that's right. Oh, break. Only on the second page of my notes. I have 8 more pages to go.
That's why you're here for the week.
Yeah. Okay. Okay, let's take a break, and then I'll come back to keep going. Thanks.